So the uniform slender bar is released from rest in the horizontal position shown. Determine the value of x for which the angular acceleration is a maximum, and determine the corresponding angular acceleration alpha. Alright, so again what we want to start off with is the free body diagram and kinetic diagram of the body itself. So let's start with free body diagram. Alright, so forces acting on this bar, so the easiest one is probably the fact that we're going to have the weight that can act through the center of gravity. So this center of gravity you would assume is sitting at the center of the bar, and it's going to have a size of mg, so whatever the mass is times by gravity. We also know that we're going to have a force acting due to the contact with the other surface. So it's going to be acting vertically upward, perpendicular to the bar, and I'm going to call this N for normal force. Okay. The other thing I'm going to mark in this diagram is the value of x, which is of course the unknown for this question, and we know that x is the distance that sits between these 2 points. Alright, so the other diagram we need to draw is the kinetic one. And this one's going to show the accelerations on the system. So first off, we know that this bar is going to rotate because that's what we're looking for, how fast it's going to rotate. So I'm going to assume that this bar is going to try and fall off this way. So that's going to be the direction of alpha. Okay. We also know that this center of gravity position is going to move, so as soon as you're having that position move, you've got a linear component of the acceleration as well. So I would expect that this is going to try and fall down and kind of make a arc shape. So that's going to mean we have both a kind of x and y component, or, as is better to think about it, a normal and tangential component of that acceleration. So we know that it's going to be rotating about this point O, where it's in contact with the ground. So our normal component, which I'll call MAN, is going to point back toward that point. Okay, so this is kind of like the normal direction here. The tangential direction is 90 degrees to it, and it's going to be the direction the point actually moves in. So this becomes MAT. And the advantage of calling it the normal and the tangential components, as opposed to the x and y components, is that we're able to provide some more kind of equations around that. So for example, we know that tangential acceleration is equal to alpha cross r, or if we're just going to deal with it in terms of the magnitude, we can write this as just alpha r. And remember that r relates to the distance between your point of interest and the one it's rotating about. So in this case, r is just going to represent the distance x. So we can write this as m alpha x. For the normal component, we can do the same kind of thing. We know it's equal to omega cross r, or if we put it all together as just a magnitude, it's going to be equal to omega squared r. And again, r is the distance between the point you're interested in and the one it's rotating about, which it corresponds to x. So we can write this as m omega squared x, sorry. Alright, so this becomes our complete kinetic diagram. Now we just need to go ahead and relate together the forces and the accelerations through our governing equations. So let's start off by summing moments this time. And I'm going to sum moments about the center of gravity g, although you could quite possibly do it from a bunch of different other places as well. Alright, so if we're going to sum moments about point G, the only force that's going to contribute a moment is the normal force, because the weight is acting through the point G. So the moment due to N is going to be N multiplied by the distance, which is just x, and the direction, it's going to cause a clockwise moment, so it's going to go in as a negative value. So we just need to equate this to the kinetic diagram. And this time we obviously know we have some angular acceleration, so we are going to have to work out what I bar is. And if you look at the tables, either in the back of your textbook or you can Google them online, The equation for I about the center of gravity for a thin rod is 1 on 12 ml square, where m is the mass and l is the length. So we're not given either of these properties, m or l, so we're just going to kind of leave it in its general form. You can see up here that they called the length in here l anyway, so that's fine. So putting this in, it's going to become 1 on 12 ml squared multiplied by alpha, and here we've drawn alpha to be in the clockwise direction, so it's going to have to be a negative in the equation. So if we multiply everything up to one line, so basically move this 12 up and simplify it a little bit, we end up with 12 and x is equal to ml squared alpha. Alright, so what we've ended up here is an equation that relates together x and alpha, which is kind of what we wanted, because if we scroll back up, what we're looking for is the value of x for which angular acceleration is maximized. Okay, so, you know, we've related together the two properties of interest there. Unfortunately though, in this equation, we know that 12 is a constant value, x is one of the things we're trying to relate together, m is a constant value, l is a constant value, but n, the normal force, is also going to be dependent on alpha. And we're going to need to sort that out before we start to try and work out what the maximum value of alpha should be in terms of x. Okay, so let's work this out, and we can get it from summing forces in the y direction, because that's going to obviously include n. So we're going to have n going up minus mg is equal to the mass times acceleration in the y direction, and we can see from here it's going to be this here, which is m alpha x, and it's going down in the y direction, so it should go in as a negative value. So if we rearrange this, we end up with n is equal to mg minus m alpha x. And this is what's going to have to go into the equation. So I might just factorize this out. And let's put it in. So we're going to get 12nx is equal to ml squared alpha, or this. Okay, so we end up with m on both sides of the equation, so they're going to cancel with each other. And if we expand out the bracket, got an x out here that needs to be multiplied in, we end up with that. And we want alpha in terms of x, so if I factorize out alpha, it's going to be L squared plus 12x squared. Like that. Alright, so now we have an equation for alpha in terms of x, where everything else in this equation is constant. So the 12 is constant, g is constant, and L is constant. Okay, so it's asking us to find where alpha is maximized, and we're going to be able to use derivatives to do this. So if we take the derivative of alpha with respect to x, we should be able to then set this to 0 to find the turning point. So to make this a bit easier to apply the derivative rules, I'm going to take the bottom line up and raise it to the power of -1. So I'm going to apply the product rule where this is u and this is v. And remember that the product rule is y dash is equal to uv dash plus vu dash, where you start off with y is equal to u times v. So I'm going to hold this the same and take the derivative of this to become v dash. So it's -1 L squared plus 12x squared in the bracket, minus 1 off the power, and times by the derivative of the bracket. So this is independent of x, so its derivative is 0. This is dependent on x, so it has a derivative. It's going to be 24x to the power of 1. So now holding this side the same, and multiplying by the derivative of this, which is just going to be 12g. So let's clean this up a little bit. Oh, and we had 24 up here, which is going to get multiplied in. So that's going to become 288. And we have the x squareds multiplied by each other. Cool. Alright, so that's the derivative, and we need to find where this is equal to 0, because that represents the turning point, or the maximum in the equation. So now we just need to solve for where the x occurs. So if I flip this to the other side, okay, so I've ended up with g's on everything, so they're going to cancel with each other. And on the bottom line here, basically what's going to happen is that can cancel with that. So basically we've lost one of these terms and it's cancelled with this one here. So if I put everything on the top line, we end up with that. And if we go ahead and try and solve this, I'm going to expand out the brackets. Okay, put the things with x's together. And we want to try and get x equals. So this is what it becomes. L on square root 12. So this is one answer we were looking for. So the value of x needs to be the length of the beam divided by the square root of 12 in order to maximize the value of alpha. So if we scroll back up here, this needs to be L on 12, square root 12. So now we just need to figure out what alpha this actually corresponds to, and of course we had our equation for alpha way back up here that we can substitute in. So if we know x, we should be able to find alpha. So the equation is this. So let's go ahead and substitute into it. Okay, so you can simplify it a little bit. If you multiply, 12 divided by square root 12 I should say, it becomes 3.464, and you're just going to be left with g and l. This bottom line, you're going to end up with L squared on it, so 1 plus 12 on square root 12 squared just becomes 2 L squared, and then you can cancel this with one of these and simplify the number down. And that's what you end up with for your value of alpha as a maximum. Alright, so that's all there is for this question. I'll see you in the next video.